Hello and welcome back to the Inside Java podcast, the podcast about everything Java, brought to you by the team at Oracle that builds Java. My name is Nicolai Parlog, and this episode of Ask the Architects is a conversation with Roberto Lozano, compiler engineer at the Java Platform Group at Oracle, that we recorded at JavaOne in March 2026. Roberto works on the HotSpot just-in-time compilers C1 and C2, and this was my opportunity to ask about all the terms that get thrown around when we talk about them. Tiered compilation, speculation and traps, inlining and constant folding, and so many more. Roberto explained how these and other analyses and transformations work. We talked about heuristics and trade-offs, and even a bit about outside contributions to the JIT and how his team works. Enjoy the episode.
Okay, I think before we get started, why don't we talk a little bit about how JIT operates, like on a big picture, and then we can go into specifics.
Sure, we can do that. So if we think about the JVM, right, as many people are aware, the way we compile and run code in the JVM, basically we compile Java code to bytecode, right, ahead of time, and then we give this bytecode to the JVM, right, and then the JVM is going to execute the bytecode, right. And when doing that, there are different ways you could do it. The most basic way will be interpretation. And interpretation is basically you take one bytecode at a time, right? Run it, then the next one, the next one, the next one.
That's when the JVM really acts like as a virtual machine, right? Like as like kind of like automaton, just
yeah, right. That's some kind of classic virtual machine setup, right? And you could do without JIT compilation. You could just do with this setup, right? It has the advantage that also it starts executing the code like really as soon as it gets the bytecode, right? You don't have to wait for anything. That's a good advantage, but it's painfully slow, right? It's very slow. So the alternative to this is to just-in-time compile the code, and there what we can do is that we can take larger chunks of bytecode, right? Like hundreds of them, thousands of them at the same time, analyze them together, and then as we are executing the application, compile this into machine code, right? That is very efficient. And then we see more of the bytecode, more of the context, and we can apply more optimizations. And so the result is that we get highly optimized, machine code to the same level of optimization you would get with like an ahead-of-time compiler like GCC or LLVM or something like that. And then you execute that instead of interpreting. So that is just-in-time compilation in a nutshell.
And that happens like just in time, meaning like it happens when it's needed, right? Like when you know that you're executing that code.
Right. Right. It happens when it's needed. It happens concurrently to the execution of the application. So after you start executing the application, right? That's the boundary between ahead of time and just in time. Time really means when you start executing the application.
Okay, So how does the JIT know what to compile them? Because it doesn't compile like everything in one go, then you might as well do it ahead of time. Like it picks and chooses, right?
That's a very good question, actually. You could still choose to compile everything, like all the bytecode in a just-in-time setup, and it will give you some advantages, but it will be quite an overhead, right? It will be too prohibitive in most cases.
Okay.
Right? So you don't want to do that in general. You want to focus on the bytecodes that really matter. Right? And the mechanism that we have in the JVM and all the runtimes is that you profile the code as you execute it, right? So that's also part of interpreter. We refer to the interpreter as interpreter, but it turns out it's also profiler, right?
Okay.
So as it is executing your bytecodes, it is recording, how often these bytecodes are executing, this loop, how often is it run, and so on.
Okay. And
then with that information, we can select the core bytecodes or methods, if you want, that really deserve to be just-in-time compiled. This rule, the 2080 rule in software, right? That 20% of your code accounts for like 80% of execution time. That's a rule that applies in many contexts and so on. And it does apply in Java as well, right? So there will be often like a little click or core of your program that, where most of the execution time is spent. And that's what you want to just-in-time compile, and not the rest, right? You can say it as a investment, right? You have to pay something, right, in order to get something. So you want to pay as little as possible to get as much benefit as possible.
Most bang for the buck.
Yes.
Okay. So then let's talk about a few common terms, right? Because we already mentioned what just-in-time means, and interpreter and profiler, but there's more going on, right? With terms. I know that there's stuff like one of the terms that we occasionally hear is like escape analysis, but there are more, and I think it deserves to spend some time on each of them. So I don't know, what would be a good one to start? Maybe
I can tell you if you want about tiered compilation. That's a slightly obscure term that many people hear and wonder, what is this tiered compilation thing?
Yeah.
It's quite central to how HotSpot or the JVM works, right? So I gave you a simplified like model or picture of how the VM works. In practice, as always, it is more complex, right?
Yeah.
It turns out that we don't have just one just-in-time compiler. We have two of them, right? And they're complementary to each other. If you want, they have different strengths and weaknesses, right? So, and we call them, not very creatively, maybe we call them C1 and C2, right? The compiler 1, the compiler 2.
And those are like really old, right? Like those are like they're almost as old as Java.
Yes, as long as HotSpot, almost, yeah. I mean, HotSpot was born with just-in-time compilation in mind from the beginning.
That's actually the reason for the name, right?
That's why it gets the name, right? The hotspots. These are the bytecodes, that I was talking about before that deserve to be compiled. Those are the hotspots in your code, right? Okay, so we have C1 and C2. You might wonder why. The thing is that there is no just one just-in-time compiler or one way of doing just-in-time compilation that fits all the needs, right? So we have a trade-off here between the performance you get from just-in-time compiling the code and the amount of effort you need to spend in just-in-time compiling that code, right? So in this trade-off, C1 and C2 are positioned quite differently. C1 is like a lightweight compiler. It operates quite quickly, okay? And it generates code of decent quality. It means, that it's going to be like 1 order of magnitude faster than interpreting or something.
Yeah.
That's good, right? But it doesn't get the peak, the top performance,
Okay.
But it does a good job. There is also this other rule in compiler development. The 2080 rule applies also to compilers themselves, right? So there are 20% of the compiler optimizations get you 80% of the peak performance, right? And then there's a whole bunch of additional optimizations you can throw in to get, to like 100% of peak performance. C1 only does this, 20% little thing, and gets you that. And C2, on the other hand, it takes considerably longer, but it goes all the way, and it does, as best as one can do to get you the best peak performance. But it means it takes longer time, right? So,
can you give us like a rough estimate, or just more like a gut understanding of what the relationship between those times and also what the effect is? Like, does C2 take twice the time, 10 times the time? I know this is probably going to be very different based on all kinds of environments, but just like as a rough idea,
more than twice.
Okay.
Maybe less than 10 times.
Okay.
But it depends quite a lot on the code that you're compiling and so on. If C2 detects that there is an opportunity for doing something really good, then it's going to invest a lot more time in compiling something. So you see, it's hard to tell in the general case how long it's going to take. Okay. But it takes longer. It's like single-digit, slowdowns of C2 compared to C1.
That's already good. I think a good ballpark. And then follow-up question, basically, about the additional performance improvement. And again, I'm sure that it's also like a wide range, as you said. Like if you find a good optimization that is worth it, it will probably will lead to performance that is much better than the C1 compiled code. But also, like you said, C1 roughly an order of magnitude faster than interpreter. And C2 compiled code to C1 compiled code, how do you think that's like more like 20%, 2 times that, something like that?
Yeah, it could be something like from 10% to twice as fast. But this is a very rough figure. Again, it depends a lot on the application, on the optimization opportunities that you have and everything.
Yeah.
Like if you write Java code like you write C, you will not find as many optimization opportunities maybe for that code, right? And C1 might do. In fact, sometimes we detect methods for which we know at runtime this is not even worth compiling with C2, like getters and setters, for example. We don't even bother because there's nothing you can get out of there in terms of performance, right? So we might as well delegate that to C1 and do it quickly.
That makes sense.
But there's one more thing if you want to know about tiered compilation that I think is worth mentioning. And this is not known to everyone as well. So the mechanism is that we start interpreting the code, profiling, as I said before, right? Once we find something that is becoming, hot, code that we detect that is being executed quite often, then we do a C1 compilation of that code. But the result of the C1 compilation is still instrumented with profiling support. So we continue profiling that, right? And this, at the end of the day, is one of the biggest benefits of C1. It allows us to start profiling at, 1 order of magnitude faster.
Okay, yeah.
Because actually understanding, what is worth compiling, it's a big part of the just-in-time compilation process itself, right? So it takes quite some part of the warm-up time to just figure out what is worth compiling with C2.
I never thought about that.
Right? So C1 allows us to gather profile information much faster. Right? And then finally, we feed this to C2, very detailed profile information, and then we do as best as we can with that.
Okay. So I'm going to just ask you about all the terms that are flying around in my head. One thing that pops in my head a couple of times already was inlining, but I want to get back to that in a second. Something that you just said about C2 being more aggressively. I know that there's a thing called like a trap. I know that one thing that C2 does is it's basically like if it sees like an if that goes like into the true branch like all the time, it will just say, I'm sure it's going to be true forever. And it basically elides the whole branching operation because like modern CPUs benefit from like having a deep pipeline of instructions being there. Can you explain to a layman like me, how does the deoptimization? Oh, maybe that's also a term that we need to cover. Like, how does it work? Like, it basically speculates it will always be true, but then if it turns out to be false, Java will still do the right thing. Just in that specific circumstance, we do it very slowly.
Right.
So can you explain how that works?
Yeah, that might sound a little bit like magic. Honestly.
Yeah.
So we said that C2 has very good profiling information at its disposal, right? And because of that, it is able to play bets with your code, right? To speculate with your code. It is also able to do that because we have this fallback mechanism that I will explain in a second, right? That allows you to go back and execute, all the code, right? So C2 can focus really on the code that matters most and also play bets or speculations on top of that because it knows there is always like another mechanism, a fallback plan, right? To execute the code bit. Like it could be C1 code, but in the case of JVM, we always go back to interpreting the code, right? Okay. Interpreter takes care of any kind of bytecode shapes that you might think about, right? Any kind of code. So we can always go back to interpreting if we detect a situation where we have speculated and we lost. So so speculation, as you said, we gather profile information about what's going on, and if there is like a branch, that's a classical example, right? If there is an if then else, and then the else is never taken or so, then we place a bet. Okay, this is that code. This code is never going to be executed. We compile just the branch that is always taken, and we leave this trap there in the compiled code. The trap is kind of a check. Is my assumption really true for this case? Does my assumption hold or not, right? And if it holds, then we go on and we execute the code like that. But if it turns out when we're executing the compiled code that this doesn't hold, then we have to go back to this interpreter safe mode, right? Get us out of here, right?
Yeah.
And so this is what you refer to as the optimization, right?
Yeah. Before we get to that, I still don't understand how the trap works because isn't then the trap still an if? Because it still seems to me like it's still a branching operation, right? How is the modeling the if as is has the downside, as I said earlier, like they have this branch and then the CPU will have to the pipelines in the CPU, whatever. But then it feels to me, okay, now the C2 compiler says, okay, we're only going to take the one of the branches. We're trying to get rid of that if. But isn't the trap just another check?
Yeah, yes, we need to do some kind of check.
Yeah, right.
Right, that's for sure.
But why is it faster then?
Why is it faster? Because sometimes we can come on that check and you reduce a single check for many speculation points, for example.
Okay.
Another one is because assuming that only one path is going to be taken, that can trigger or create opportunities for many subsequent optimizations as well.
Okay.
Right?
Oh, so does that mean...
Think about that. If you have like a very complex loop, right? But it turns out all the complexity is a branch that is never taken.
Yeah.
And then you can add a check. Maybe you can even hoist the check out of the loop and perform it, before the loop is going to start. Okay. Not every time you run the loop, that is already a big win, right?
Yeah.
And on top of that, maybe then the loop gets very much simplified, and maybe you can do really cool things with it all of a sudden, right? Maybe you can vectorize it, or maybe you can unroll it, or maybe you can whatever.
Yeah.
Right. So it uncovers many optimization opportunities, and also you can typically reuse it for different contexts, and also typically you can move it around to a cheaper place where it is cheaper to execute.
Okay.
Right? So in practice, these checks are not very expensive. We have even more low-level dirty tricks, to reduce the cost of these checks, but I don't know if you're interested.
We'll see, because we already every answer uncovers like a whole things to ask about. So you just said vectorization is something we could talk about. We want to talk about deoptimization, hoisting. So we got like a lot more terms to go over. So maybe let's continue the thought about what's the deoptimization there, right? So let's say the trap closes and we realize, this optimization didn't actually work.
We're executing a path that we speculated we never would execute, right? Then what we have to do is, remember, we are in just-in-time compiled code, right? But we still need to know where would we be if we were executing the same, bytecode by the interpreter. So we need to be able to find a way back to interpreter, to state in the interpreter that corresponds to the same state as in the compiled code.
Yeah.
right? So that's something a little bit tricky, and it's something quite unique about just-in-time compilers. The just-in-time generated code needs to keep a correspondence to the original bytecode, right? It's not just for debugging. Of course, for debugging, all compilers need to do this.
Yeah.
But in this case, it's also essential for correctness, because sometimes you need to go that way, right, from compiled code. So what we have is we inject in the compiled code synchronization points, where we know exactly what the corresponding state, what we call the JVM state, basically, how would the bytecode stack look like, what would be the locals and things like that at this point. And then if we end up in one of these traps, then we consult this state and then go back to the interpreter and then recreate the state. So we trick the interpreter into believing that we were here, continue executing, please.
Yeah.
The interpreter would never know.
Yeah. So that also explains why it's so slow, right? I guess like building that is probably taking some time.
Yeah. I mean, building and maintaining this takes time, but also the act of deoptimizing itself can be a little bit slow.
Yeah.
Because we consider it to be like a rare event, right? Think about exceptions is a good case. Often we speculate an exception is not going to be thrown, right? And then we might have check like that too. And if it is thrown, then we might have to deoptimize, go back to interpreter. Right, but it's supposed to be an exceptional situation, right? By the name, it's an exception.
Yeah.
So that's why we think it's it's okay to pay that cost at that time.
So just to point that out, you said to synchronize earlier. This is entirely unrelated to like thread synchronization. It's really just like just a marker point.
Yeah, think single thread. It's just synchronization between the machine code that you are generated by the just-in-time compiler and the state of the interpreter.
Yeah. Okay. You mentioned hoisting. What's that?
So this is a general term in compilers, not just-in-time compilers. In fact, it's kind of an optimization, right? So one thing a compiler can typically do is it can move code around, right? Maybe you are performing a computation at the loop, but maybe the computation doesn't really depend on the loop indices or anything. Maybe it is loop invariant, what we call. And in that case, we should be able to actually move it, perform it just once before the loop.
Yeah.
Right? That is hosting, basically.
Okay.
So hosting is the act of executing the code earlier than in the original application, right? If that gives any performance advantage. And then there's the opposite term of syncing, executing the code later in the application, if that gives any advantage.
Yeah.
Right? And the compiler tries to figure out, is it a good idea to hoist this code at this point, yes or no, and so on. Based on, for example, information about how often is each code path executed. Right?
Okay. It also sounds like just coming up with, it feels to me like these things are not really easily deterministically decidable. It's not. To me, it seems like it's not obvious that which optimization where will exactly like result in what. So it seems to me like it's a lot of like on the side of like the JIT programmer like you. It seems maybe I'm wrong though. Correct me if I'm wrong. It feels like, is there a lot of experimentation there? I guess. Like, do you always like when you want to do something? It's not always obvious. I would assume that this optimization will make things better because as you said, like maybe hoisting or syncing, you could turn out like, no, it doesn't actually do anything, or like it adds.
Right, exactly. So when you are doing an optimization, there are several limitations. I mean, for which the optimization, you might not be able to do the optimal thing, like the best thing, right, in all situations.
Yeah.
One of them is that, sometimes the algorithm that really does the best thing is too expensive. Like many computational problems in compilers are, NP hard and so on. So just because of that, sometimes you need to resort to, approximation algorithms that try their best, but sometimes might not do the best possible thing. And another one is because we are working with imperfect information, right? We're working with profiling information captured at a certain point of the application, but might not hold anymore, at a later stage of the application execution or something. So yes, so what we do there is we resort to what we call heuristics.
Yeah.
Right, and in developing these heuristics, which is basically, rules of thumb for the compiler, when does it make sense to do this and so on, there's a lot of experimentation.
Okay.
So there are lots of, magic constants in the compiler. We'll say, if this thing is more than 3, then do it. Otherwise, not.
And so, how do you figure those out? Like, you just run like those the JIT against, like while you're working on the JIT, you just precompile it and just running against like a whole host of Java applications and figure out whether it works.
Right. I mean, we start with some form of mental model of what's going to be the performance benefits of a certain optimization, and you develop and refine this mental model over the years, trying to anticipate what the processor is going to do with this particular code, which is, by the way, becoming more and more challenging these days, right? Because processors are so complex.
Yeah. They're also doing a lot of what you're mentioning, like under the hood again.
Yes. Yes, exactly. Sometimes we are fighting in different directions, and it's hilarious. But anyway, where were I?
I was asking about that when you're developing the JIT, how do you figure out whether something is actually better?
So we start with some understanding, some model, but it's just a model, right? We need to validate it with experiments. So we do lots of experiments with different factors, different parameters, adjustment, and so on. There's quite some work of tuning there.
But what code bases do you run it against? Like, is there's like a spec JVM kind of like benchmark thing, or do you run it against regular applications? Like, I don't know, like
both.
Okay.
Both, yes. I mean, we definitely use all the standard Java benchmarks that you might think about that are out there, but we also do benchmarking on some internal applications. Yeah, benchmarking is always a challenge. Right?
Yeah. Okay, so two more things. I know one thing that's very important, and I actually do have a pretty well understanding, I think, what it is, but you can probably like enlighten me. It's like inlining. I know that's like, it's often called like the mother of all optimizations. Right. And then escape analysis, because that one can lead us to our next topic that I want to ask about. But let's talk about like inlining first, what that is and how it's applied.
Right, so I said at the beginning that the just-in-time compiler has this big advantage of being able to compile multiple bytecodes at once, so it can see more of your application, right? It can see like an entire loop or an entire set of nested loops or something, while the interpreter only sees one bytecode at a time. It's like a peephole, where it's looking at one bytecode at a time, right? Inlining is an optimization that kind of doubles, the effect of that by not just looking at one method at a time, but a set of related methods, right, that call each other and so on.
Yeah.
So basically, by looking at more methods, and you have more opportunities for optimization.
Okay.
Right, especially in the case of Java, where the typically good practice of Java is like small methods and lots of abstraction and so on, right?
But that doesn't mean, like, let's say I have a method that calls like 3 other methods. And then what you described to me, it sounds like, well, we're just going to assume it were like one big Java method, and then we're going to compile it all as one.
Yes.
But in source code, though, it is still 3 methods, and I could call one of them on a different path. So does that mean that the machine code for that method basically exists like multiple times?
Yes, inlining might lead to duplication, yes.
So that's, I guess, then a trade-off, right? Because like inlining is not like we're inlining, because it's not like we're inlining the entire...
There's definitely a trade-off. Inlining, I mean, the performance profile of inlining is typically that, the more and more you inline, and typically you see the performance improving.
Yeah.
But all of a sudden you get to a cliff, and it's like, boom.
Okay.
You die. So you need to be very careful there with over-inlining, and just because of that, you blow up the instruction caches of your processor and so on. So there is definitely a trade-off there.
Yeah.
So you need to make really sure that you inline what matters.
Yeah.
And the good thing about our JIT compilers is that we have very good profiling information again. So if we have this method that is calling these other 3 methods, then we have information about how often are we calling these 3 other methods. Maybe we're calling one of them in a very hot loop. We definitely want to inline that. But the other one maybe is we only call it every so often. Maybe we don't bother inlining it because there is such a trade-off.
Oh, so you don't. Interesting. So when you take a method, that means, as I said, it calls the other methods, and then that doesn't mean that either you inline nothing or inline everything it calls. You can basically leave like escape hatch will say like, okay, this one will call out to the actual method, and the other 2 we're going to inline and optimize together. Interesting.
Right. Exactly.
Okay.
So and another factor something we take into account is try to predict the size of the code after inlining, right? So maybe I have this call to a method, and it might be a good idea to inline it, but maybe it turns out that this method is huge.
Yeah.
Then in that case we might even not inlining because of what I said. The cost will outweigh the benefit in that case. So there is a lot of heuristics again in this space.
But then also, don't the heuristics depend on the processor you're just in time? Because that's one chance of just-in-time compilers that you don't need to be general. You know like what exact machine you're running on, so you can like optimize for that. But that wouldn't that mean that, well, this Intel does it this way, and that AMD does it that way, and then it's like, there's just more ifs and else's and branches and magic constants.
Yes, it is like that. So you might have different results if you run in different families of an Intel processor or whatever, because we take into account the size of inline caches and whatnot to adjust this heuristics, right?
How terrible is the code in the JIT? Because like what you described sounds...
Next question, please. No, I can take it. How terrible it is.
It sounds like a ton of magic constants and like just trying like heuristics, as you say, like, okay.
Right, exactly. I mean, we try to abstract as much as we can, but you can imagine that, this is code that has been there for decades, right? We have lots of contributors contributing into our JITs. it's not just Oracle as the stewards of OpenJDK or a small clique of developers working on our JIT compilers. It's basically the entire Java community doing it. So that is great. That is amazing, right? But from the code complexity point of view, doesn't help. So yeah, it's a challenge to maintain the complexity of balanced and so on. But we do our best. So what we do is, for example, we revisit optimizations every now and then. Right? Some optimizations might have been really important 10 years ago. Maybe they are not important anymore because the hardware has evolved, or the libraries that depend very much on that optimization, are using some other abstraction and not capitalizing on this optimization anymore. So then we try to clean up a little bit around that area. So yeah, we try hard to maintain. We have actually invested a lot the latest years on the maintenance aspects of how we did compilers. So for example, from a testing perspective, we have now pretty powerful frameworks for testing regressions in the compiler, not just functional regressions. We have always have that. But also performance regressions.
So when you say functional regressions, that means like the guarantee that the code that is generated must still be correct.
Right. I mean, we have always had that because that's the number one goal, right? But what we are becoming better at, for example, is detecting whether this little new code that I added, did it actually inhibit or did it break somehow any other optimization that the compiler used to do or something like that. We weren't very good at that like 10 years ago or so, but we are in a much better position now. With help of tooling and testing and so on. Another important tool for us is fuzzing these days. Fuzzing has become like a standard testing technique for compilers in general, and also in our context. Should I explain fuzzing, or is that obvious? Basically, you generate randomly, like in this case, programs, right? Input. In this case, we generate random Java programs, like massively, right? And then we run them, we just-in-time compile them, and then we compare them to the execution of an interpreted. So just interpreted only, as the kind of ground truth. And then see if we generate the same code or not. And these techniques are very useful at finding, corner cases or optimizations that might have been, disabled by mistake or things like that. Because as you kind of hinted yourself, compiler is a very complex system, right? And the complexity arises from very many ways in which different optimizations can interact with each other.
I can imagine.
Right, so it's very hard to cover all that space from testing, just from manual testing, right? So we resort a lot to fuzzing these days to kind of explore and exercise this search space more exhaustively.
Another thing that I realized right now, specifically the interest, that's something that pops up with the lazy constant API now. Something that gets mentioned a bunch, which is constant folding. Also, I think a pretty old optimization, which again, I think I have a rough understanding of what it does, but you can probably help me out. What does constant folding do, and why is it helpful?
Right, constant folding is one of the big 8, as they call in compiler world. Sometimes one of the essential compilations that pretty much every compiler does. Right. The idea here is to detect variables which always take the same value. Right, and if you do that, then the places that use those variables might as well use this constant value that is known. Right? And that might in turn, propagate. So, now that might create more constant variables. And it might have all kinds of effects. For example, maybe you have a check, and now because you have propagated this constant value, that this number can never be positive, negative anymore, or something. And all of a sudden you can remove a whole branch or something. So constant folding by itself might not have like a huge effect, but again, it's kind of an enabler of other optimizations. A little bit like inlining in that sense.
But so constant folding, I think there's so I know that if you something like 5 times 7, and then the compiler can just figure, okay, that's 35. That's like one way of constant folding. But Java also constant folds like loads or references, right? Like when I have like one object calling the other, and specifically again in the context of the lazy constant API in Java 26, or like the current preview to Java 26, we have to talk about that this reference chains to like final fields, that they get like collapsed right into just one read. Like how does that work exactly? Can you describe that a bit?
Yeah, to be frank, I'm not super familiar with the lazy constant API. But basically, once you tell the compiler, once the compiler is allowed to assume that a certain variable has a certain known value, right? Then it can use it, like I said, in many different contexts. So maybe maybe you have a Boolean, right, that is like print debug information or not in my application, right?
Yeah.
And if the compiler is allowed to, exploit the fact that this Boolean may be, false, then you can get rid of a whole lot of, debugging code in your application and not bother compiling it and so on.
Okay. But so escape analysis also doesn't only apply to like primitives, what you constitute primitives in Java code, but also to like the references or like potentially like the
Sorry, you said escape analysis? You mean?
No, sorry. Yes, I was already meant. Yes, no, I mean like constant folding. So it doesn't necessarily only apply to like primitives as we discussed, like the Boolean example, for example, but also like if it knows like this reference always.
Right. If it knows this object is always going to have the same value, then you can go ahead and reuse that or use that information for many. Like anytime you have a load from a field of that object, then you might as well replace the load with a value that you know is going to be in that field, right? Because it's constant.
Yeah. Okay.
So definitely, yes, you will save memory bandwidth, which is becoming more and more and more important.
Okay.
These days.
Oh, right, because the difference in speed between processors and memory keeps growing, right?
Right. Yeah. So if you can remove loads and stores and so on, that's a big win usually.
Yeah. So that's how I understand like lazy constant API. Basically, it allows. It's not like the API itself is not really important here. It's just like that brings up the topic of constant folding a bunch of times. But so it talks about constant folding across like final fields essentially. So like that instance is always that one, and that one has a final field that is always that one. And then if you can really trust those final fields, which you can't at the moment, at least not generally.
Right, damn it.
Yeah, but soon. Like this is.
Yes, please.
Yes, it's Java.
Let us trust.
Yeah, soon. Okay, so then let's get to escape analysis because I already brought that up a couple of times. What is that doing, and what's the benefit of that?
Right. So escape analysis is an analysis, like the name says, right? In compilers, we perform two types of actions, right? We do analysis and then we do transformations based on the result of the analysis, right? An analysis doesn't do anything by itself to the program. It just collects facts about the program. It tries to learn something about the program.
Okay.
Then a transformation exploits those facts, right? To optimize the program, to transform it in some way, make it faster, typically. Yeah. So escape analysis is just an analysis by itself. The important thing is that this analysis enables quite some powerful optimizations. And perhaps the most powerful optimization is scalar replacement.
Okay.
Right? So maybe I can start by explaining what scalar replacement is before, and then I can explain what the compiler needs to do to get there.
Sure, yeah.
So scalar replacement basically tries to look at objects that the compiler is allowed to decompose into the primitive fields, or into the individual fields, sorry, not primitive, and then treat these objects as if they were just an aggregation of those fields, right? So in terms of Java code, you might imagine that you might have an object, and instead of allocating a new object, you just create a bunch of locals, once for it, one local for each field of the object, right? And then you operate on those locals instead of creating the object itself.
Yeah.
Right. So that's very powerful because all of a sudden you don't need to allocate in the heap, right? Allocating in the heap, even though we have these amazing garbage collectors, right? It's still expensive, or it's more expensive than not doing it.
Yeah, definitely. Yeah.
Right. And then every time and then these locals that you create instead, they're going to end up being stored in the registers of the processor, or in the very worst case, they're going to be stored in the stack.
Yeah.
Well, in either case, better than the heap from memory efficiency perspective and so on.
But also just memory efficiency, also just the CPU speed, I guess, right?
These days one thing is the other, really. So memory efficiency, it's all about memory efficiency. But yes, this is going to give you speed up, right? And so that is one amazing thing, but there's even more, because once you transform these allocated objects into a bunch of locals, then the compiler can see through those. Then it can reason individually about those, right? Okay. So this can in itself, trigger many other optimizations or enable many other optimizations.
That's a recurring theme, right? That one optimization can allow others to take place. Interesting.
So scalar replacement is very interesting because it is both an enabling optimization, but it also creates a lot of value by itself by removing the allocation, right? So it's a big win when you can do it.
Yeah.
Right? But the problem for the just-in-time compilers is that we cannot just do it everywhere or whenever we want. We need to perform some analysis, to make sure that we are allowed to do it.
Yeah.
Right. And here is where escape analysis, gets into the game. Right. So escape analysis looks at an allocation of an object, and really at the whole lifetime of the object, right? Every time the object is, loaded from or written to, and so on.
Yeah.
The whole lifetime of it, and then it reasons about, could it be so that, for example, another thread can see this object and maybe store into this object, into field of this object? Or could it be so that a method that I'm calling might change the state of this object? Because if so, then we are not allowed to scalar replace it anymore. We would say that
I can already see inlining being said again. If the other method is not inline, I don't know what it's doing, right? So I have to assume that it does something.
Exactly. It has a very, very tight connection to inlining. Right. So we say that if we are sure, if we can prove that this object is not going to be accessed anywhere else, then we say the object does not escape. Right?
Okay.
Otherwise, we say
so escape is like, so I have a scope and it escaped. Like if it goes outside, then I don't know what's going on.
If someone else can do something to that object, right, without you knowing, that's kind of the game, right? And otherwise, you say it might escape, and if it might escape, then you cannot do anything. Right? You need to be safe always. So yes, inlining plays a vital role in here, right? The way we inline determines pretty much what we can do in terms of escape analysis. Yes.
And the reason why that escape analysis is so interesting is that, so basically I think what I get from that is that it's the object more than just a collection of fields. And Java now uses the term, in the rise of Valhalla now uses the term identity for that, right? Does the identity matter? And that's where value types come in and say, no, identity never matters for us. Right. So does that mean that escape analysis not for records, that's wrong, for values, for value types, whatever they're going to end up exactly being called. Does that mean that escape analysis for values can always say, does not escape? Like by default, there's no such context?
Because of the lack of identity, but also because of the immutability of the value objects. Right? With these two properties together, there is really no escape analysis anymore to be done. I mean, you can just do it. You can always scalar replace through value object. There's never a reason why you can't, in theory at least, right? So there is even no need for escape analysis anymore for value objects, right? We will scalarize them.
Okay.
So that saves a lot of headaches for us.
Nice.
maybe even important to remark in the context of value objects, the way JEP 401 is looking now. Also, we are decoupling scalarization there with inlining. So no matter what you inline, we will be able to scalarize the value objects. That means even if we are passing,
good point.
Even if we allocate a value object and then we pass it to a method that we don't compile together, that we don't know anything about, we will be able to scalarize that object and then pass it really as a bunch of fields, if you want, instead of passing it, the reference to it.
Yeah.
And so we will scalarize it by construction as well.
Yeah.
Right. So that makes a whole difference for how effective scalarization can be, right? Because you don't depend anymore of the somewhat arbitrary decisions of the inliner. You are not at the mercy of the inliner if you want.
That also brings something interesting that I think is important for people to understand when they think about Valhalla, which is Valhalla is going to enable a ton of optimizations. Valhalla doesn't necessarily come with all of those optimizations. It's more like it gives guys like you a lot of more room to do good work in the future.
Right.
So that means that performance characteristics of value types will improve over time. And the fact that it doesn't have like all of the optimizations on day one is basically by design. Like it's not possible to have all of that. It's just,
right. We have started with scalarization, from the compiler perspective, because this is like, again, applying the 2080 rule. This is the optimization we see most potential on, but there are a whole bunch of other optimizations that you can do.
Yeah, okay. So we covered a lot of ground. Towards the tail end, I want to cover like a few different things. So one thing that you mentioned that I thought was really interesting, you said like that there's a lot of companies contributing to that. It's not just Oracle's doing everything, which is true for most parts of OpenJDK. But the way you described it is, so it's true for most parts of OpenJDK. I mean, that Oracle is not doing all the work. But the way you described it is like these other companies really playing like an important role, because I can assume that somebody like a company like AMD or Intel probably has interest in getting Java to perform well on their CPUs.
Right, exactly. So if you take, for example, hardware vendors, they don't only have the best interest on Java to perform well, but they also have typically the best knowledge about their own hardware, right? And when we're designing optimizations, they are best placed to say, if you do it this way, this is likely to perform better in my processor, and so on. So they contribute with vital knowledge about that. there are many things about modern processors that you don't see in the specs, right, or in the ISAs.
Yeah.
The ISA is just a specification about functional specification, but you don't know much about how this code is going to perform. How is the branch predictor going to perform? Or what is the size of this or that buffer? Where are the bottlenecks in the processor and so on? But of course, our collaborators from different hardware vendors they know.
Okay.
Right? So they contribute all that knowledge.
Okay. So would you say that the knowledge is the most essential contribution, more maybe than the code?
Yeah, I mean it reflects on the code that they contribute, right? So they're not contributing code.
They also contribute code.
Yeah. So one point of contribution where we with a lot is the intrinsics. I don't know if you want me to explain what an intrinsic is.
Yeah, sure. Let's go.
An intrinsic is like a manually low-level written piece of code to implement like a common library operation.
Yeah.
Right. And when I say manually low-level, I really mean like assembly or machine code, if you want.
Okay. So that means for different CPUs then, right? So there's like
yes,
intrinsic.
Yes. You need to write one for each platform, or perhaps even for one for each family within each platform or so. Right, exactly. So you might wonder why do that, right? Why not just let the just-in-time compiler compile the Java code, get done with it?
Well, I assume because you didn't do a good enough job.
Yes.
Is it so? I assume because because you can still eke out more performance manually.
Yes. There are different reasons why that is the case.
Okay.
Right. So, for example, we have automatic vectorization of code that is great and it's becoming better and better, but it's still not all the way there compared to what a human with good knowledge of a processor can do, right? So many intrinsics are written so that they exploit the best out of the vectorization capabilities. Another example is custom instructions that are becoming more and more popular. Instruction set extensions, like an extension for cryptography or something. That's this very specific cryptographic operation for this processor or something. There's no way on earth that the compiler is going to detect this exact pattern and exploit that instruction, right? You need an intrinsic for that. So there are some fundamental reasons why these things are done. But of course, as compiler engineers, there's a little bit of an element of defeat, if you want. And also, it's not great for maintainability because, like you say, you need to write a specific version for each platform and so on.
Yeah.
But it gives so many benefits that we're pragmatic, so we do it.
Sure. I can specifically see that when you say that there's specific extension for exactly the thing you want to do. I would assume that the intrinsic is then it really gives you a lot of bang for the buck of writing and maintaining.
Right.
Okay.
Exactly. So that's one example, and perhaps the most straightforward example of place of collaboration within these JIT compilers.
Okay. So maybe as the last question or question complex, how does your work look when you do all that? It's like, do you read a bunch of is papers is ongoing research important for your work, or is it, or all the optimizations already known and you just need to apply them? So for those of you just listening, I made gigantic air quotes about just applying them.
Well, I mean, compiler development has been traditionally a very research-driven area, right? So there are tons of literature, academic literature about how to do things. It's a lot done it's one of the oldest computer science areas. Right? There's been research papers from the 60s, 70s, 80s, 90s.
Are you working with those on a daily basis? Are we that far behind? You still have to read 60 years?
I don't think we are in the 70s or 80s yet. But
what do you say?
This might be. No, sorry. No, I don't mean yet. I mean,
okay.
So you can scratch that.
So you're past the 60s and 70s is what you're saying. Good.
Yes, we passed the 80s. I would say. Then it's a bit blurry, but I would say that maybe this is controversial. But I would say definitely we're still catching up with the state of the art in research. Yeah. Not just us. This is not just a JVM or a C2 thing, right?
Yeah.
Every compiler in general, GCC, LLVM, our JIT compilers, we're still catching up. We might be in the 2000s now or so, if you want. So there is some work to do. And yes, we go back to literature often. We track the main academic venues and so on. We even on my team, we have some kind of slightly academic structure of reading papers and presenting papers to each other, just like you would do in a research group in a university.
So you can take the JIT engineer out of the university, but not the university out of the JIT engineer.
Exactly. There will always be a paper behind us.
Okay, good. Thank you. Do you have anything more that you want to share? Anything we want to get to?
No, I think we covered a lot already. I'm happy unless you have more questions.
So thank you very much for taking the time and for explaining all this to us. And maybe in the future we get together again and we go into, because even now I feel like, well, we covered a lot of ground, but again, like the one or the other term popped up that I think could do an explanation, but it really shows how much is happening and kind of also needs to happen for Java to be as performant.
This is an ongoing process. I mean, we're basically never done with just-in-time compiler. As you know, hardware changes, the library changes, Java, the language changes, the way people use Java changes, the way we deploy Java applications changes, and all of that. We adapt continuously. We add new optimizations, revisit optimizations. So this is a never-ending job. So we can talk again in a few years. There will be more things to talk about.
Yeah, thank you. Let's do that. Thank you for being here.
Yeah, my pleasure.
Yeah.
Okay.